When you stand before the Trevi Fountain in Rome, the sheer volume of water cascading over the Baroque stone feels like a spectacle of nature. But let's be clear, that water isn't arriving via modern plumbing. It's actually fed by the Aqua Virgo, an aqueduct that's been functioning for over 2,000 years. While most ancient Roman infrastructure eventually crumbled, this channel remains, hidden behind modern concrete and masonry, as the only one of the original lines that has never stopped delivering water to Rome. By the end of this episode, you'll understand the precise tools, the hydraulic secrets, and the self-correcting engineering methods the Romans used to move mountains of water across an entire empire. To grasp the scale, we have to look at the Roman water system as a monolithic industrial project. At its peak, the city of Rome was supplied by 11 distinct aqueducts, delivering over 1 million cubic meters of water every single day. Now, this wasn't just a modest supply for a town, it was a deluge intended to fuel a culture of extreme public luxury. Greek engineers had already established the template back in the 6th century BC, using stone-lined channels in Athens or tunnels in Samos. By the Hellenistic era, engineers in Pergamon were experimenting with pressurized lead pipes. But the Romans? They shifted this from a craft to a full-scale industry. They combined the architectural arch with a specific type of hydraulic concrete, allowing them to maintain a consistent slope across incredibly challenging terrain. It's staggering to realize that this wasn't merely about survival. It was about powering baths, fountains, and private villas on a scale that wouldn't be matched until the modern era. Behind those grand stone facades lay an invisible, constant struggle against entropy. The maintenance of these aqueducts was the burden of an organized, permanent staff of roughly 700 workers. These men spent their lives operating within the concrete channels, which were intentionally designed with enough clearance for a human to walk through. Though, in reality, it was a world of perpetual dampness and claustrophobia. Their daily existence involved scrubbing away mineral deposits, which accumulated rapidly, and sealing hairline cracks with waterproof cement. The efficiency of the entire city's water supply depended on these workers. If they failed to patch a leak, the flow diminished. If they ignored the buildup of lime, the channel capacity simply choked. The grandeur of Rome was, quite literally, maintained by a workforce spending their entire careers in the dark, fighting the slow, inevitable creep of calcification. A Roman aqueduct functioned as an artificial river, relying exclusively on gravity, and the engine of the entire system was the gradient. Engineers had to be exceptionally selective about the source. Lakes were avoided because the water was often stagnant and unhealthy. Rivers were bypassed because of sediment and seasonal volatility. Hillside springs were the primary target, offering a reliable, clean flow. Once the water entered the channel, the real challenge began: maintaining a steady, uniform velocity over dozens of miles. Since gravity was the only force, it required surgical precision. If the slope was too steep, the water would gain too much velocity, causing the masonry to erode and the mortar to fail. But if the slope was too gentle, the water would stop moving entirely, leading to stagnation. Consequently, most Roman aqueducts descended by only 5 to 10 feet for every mile of distance. Now, lacking modern GPS or laser levels, Roman engineers relied on two essential instruments, the dioptra and the chorobates. The dioptra was a sighting platform used to map the terrain, measuring the relative angles and heights of distant landmarks. For the critical task of leveling, they employed the chorobates, a wooden table roughly 20 feet in length with a central groove filled with water. It operated on the same principle as a modern bubble level. If the water surface aligned perfectly with the edges of the groove, the surface was level. By repeatedly using the chorobates to establish the gradient and the dioptra to map the path, they could ensure that a consistent, gentle flow was maintained for 50 miles or more. And here is where we encounter a genuine engineering paradox. Some Roman aqueducts exhibit slopes as gradual as 1 in 20,000. To put that in perspective, that means the water drops only a few inches over an entire mile. This level of precision is incredibly difficult to reconcile with ancient technology. Just look at the Pont du Gard near Nimes, a massive 160-foot-high structure built from limestone blocks without any mortar. The channel itself descends less than 1 inch over its entire length. The margin for error here is almost non-existent. If the engineers had miscalculated by even a fraction of a degree, the water would have either surged out of control or pooled into a stagnant swamp. The question remains, how did they achieve this level of accuracy without digital sensors? To manage the terrain, the vast majority of the aqueduct length actually remained underground, tracing the contours of the landscape to preserve the gradient. When they encountered a valley, they raised the channel on rows of masonry arches. Following the reign of Augustus, they transitioned from blocks of local stone to brick-faced concrete for faster, stronger construction. When they needed to pass through a mountain, they tunneled, excavating via a series of vertical shafts. But the human element was always a gamble. From what we can tell, an inscription from North Africa records a disaster where 2 work gangs, tunneling from opposite sides of a mountain, became disoriented and dug in completely divergent directions. They were fighting a mathematical war against the mountain, and at times, the mountain won. So, how did they actually achieve that 1 in 20,000 slope? Well, some researchers propose that engineers used the aqueduct channel itself as a calibration tool. By partially filling sections of the completed channel with water, they could observe the surface level against the walls and mark the precise gradient. By moving this water level forward in stages, they effectively used the water to calibrate the path of the water. It essentially turns the aqueduct into its own surveying instrument, a self-referential feedback loop that allowed them to adjust for minor irregularities in the terrain in real time. The true secret of their durability lies in the material, Roman concrete. It relied on a specific volcanic ash called pozzolana. When mixed with lime, it created a chemical reaction that made the concrete essentially hydraulic, meaning it could harden underwater and, crucially, grow stronger over time. Recent research indicates that lime clasts in the concrete acted as a self-healing mechanism. If a crack formed, water would infiltrate, dissolve the lime, and reprecipitate it into the crack, effectively sealing it. This is why these structures survive millennia, while modern concrete, which lacks this self-correcting chemistry, often degrades within decades. Now, when a valley was too deep to bridge, engineers used a physics loophole called the inverted siphon. Water flowed from a header tank into sealed lead pipes that plummeted down the valley wall, crossed the floor, and then surged back up into a receiving tank on the opposite side. The receiving tank had to be positioned slightly lower than the header tank to maintain the flow. At sites like Aspendos, this system created immense hydraulic pressure, essentially turning gravity against itself to force water across an impossible gap. It was a sophisticated manipulation of high-pressure fluid dynamics, long before modern physics ever formalized the rules. Once the water finally reached the city, the journey ended at a central distribution hub known as the Castellum. From here, the flow was managed via sluices and stopcocks, directing water through lead or ceramic pipes to public fountains, baths, and private residences. But this created a literal social hierarchy of water. The wealthy were granted direct access, while the common populace relied on the public fountains that received the remaining overflow. Water wasn't merely a resource, it was a marker of political and social status in the Roman city. Today, many of these structures remain standing, but they are increasingly vulnerable. The transition from imperial grandeur to the decline of regular maintenance left much of this network in fragments. While the Aqua Virgo continues to flow, we're left to observe how long a structure built for eternity can survive in a world that has largely forgotten how to maintain the very concrete that holds it together. The endurance of the Roman aqueduct system forces us to confront the difference between our temporary, high-tech infrastructure and their monumental, low-tech permanence. We see a system that relied not on advanced computation, but on the chemical resilience of pozzolana ash and the simple, punishing accuracy of a water-filled wooden table. The maintenance crews and their dark, claustrophobic tunnels, the engineers calculating a 1-inch drop over 100 yards, And the laborers bridging deep valleys with pressurized siphons, all of these elements created an artificial river that defied nature for centuries. We're left with the physical reality of the channels themselves, which continue to channel water through the ancient earth. The question is no longer how they built these systems, but rather what happens to our own infrastructure when we lose the specific labor-intensive knowledge required to keep it moving.